Yeah, hello, welcome to a brand new episode of again to reverse engineering, and you're welcome to the brand new episode. If you're not subscribed this channel, please like, share, and subscribe this channel. Earlier, we had studied about how to calculate the internal inductance and external inductance, and finally, we calculate the total inductance of a line. Of after like this channel is dedicated to not just to solve our gate or ESE problem, but to learn the techniques. So the techniques in the thing is very important. If you have to go ahead, you can see there is video on superposition theorem, Thevenin theorem. So it's of course a new and a fresh approach towards engineering. And please you like, share, and subscribe it so that it gives me motivation to produce time and again such videos. So let's do a problem from a competitive examination. Let's see like what we have studied, how it helps us. So this is a problem that has appeared in ESC exam, engineering service exam 2002. So already what we have studied is that part of that internal induction. So a three phase, okay, a three phase transmission line has its conductors at the corners of an equilateral, at the corners of an equilateral triangle, okay. So one important phenomena regarding reading the question is that you have to read the question with detail by taking pause, okay, with sides 3 meter, and you have to keep into account the dimensions and the units. You have to see that what it is answering. Simply before thinking, you should not ink, okay, you should think inside your mind and then start to ink. So the diameter of each conductor is 1.63 centimeter. The inductance, now it is asking the inductance, okay, of the line of inductance of the line per phase kilometer is, okay. So now it's asking you about the inductance of the line. So if we have to solve this problem, so you have to read the problem once, you have to hold the problem, okay. So now if you carefully look at the diameter, so it is mentioning the dia is, so before going to the solution, so what it is mentioning, it is mentioning d is equal to 1.63 centimeter. That means obviously our r would be equal to 1.63 divided by 2, and that is equal to, tell me, by now you must have calculated 1.63 divided by 2 happens to be 0.815 centimeter, okay. Now we know that like from our previous calculations, our r dash, the value of r dash, if we want to know the value of r dash, so r dash would be equal to, yes, tell me. So r dash is in e power minus 1 by 4 into r, okay. This in minus e power minus 1 by 4 we calculated in the previous section, 0.7788 r. So we have the value of r dash with us, that would be 0.7788 into r. The value of r is 0.815. So once we are calculating it, the total value happens to be 6.634 centimeter. Now you got the value of r dash, okay. And now the thing is that we have to see the inductance of the line per phase kilometer. So this is the question. It is asking the inductance of the line per phase per kilometer. Earlier I have told you, if we have the inductance in Henry per phase, so Henry per phase would go in Henry per phase per meter, whereas the inductance in case of kilometer was millihenry per phase per kilometer. So first of all, this is 0.634 centimeters. So in terms of meters, if we have to express this r dash, so it becomes 0.634 into 10 power minus 2 meters, okay. Because we know that 1 centimeter or 1 meter in that scenario is 100 centimeters. So that means 1 centimeter would be 1 divided by 100. That is nothing but 1 centimeter is 10 power minus 2 meter. This is elementary 10 standard. Okay, no problem. We have to do. Okay, and now we know the formula. Okay, for the inductance, what we saw. Okay, for the per phase inductance. So the per phase inductance is 2 into 10 power minus 7. Okay, ln of d by r dash. This is the formula what we saw previously. So we'll write straight away 2 in 10 power minus 7 ln of, okay, the value of d, okay, is 3 meter. So you can see over here, this is given, d is given in 3 meters. So this is the three-phase transmission has its conductors at the corner of an equivalent sides of 3 meters. So this is your distance, okay, d is the distance wherein the diameter, the conductor diameter gives you the radius. So this is 3, and that would be divided by 0.634 in 10 power minus 2. So it happens to be around 12.32 into 10 power minus 7 in terms of Henry per phase per meter. Now if you have to express the same value in kilometer, then you can express this in terms of kilometer, multiply it with the 1000. So and then it becomes it will give you around 1.232 millihenry per phase per kilometer. So in terms of kilometer, if you have to express, this is in henries, and millihenries means again you have to multiply this, okay, and the kilometer stuff will also come, and the total for the meter 1, because 1000 meters is equal to 1 kilometer, and 1000 henries is equal to, so you have to multiply this with 10 power 6. So when you are multiplying it with 10 power 6, so 10 power 6 and 10 power minus 7 will be left with 10 power minus 1. So that 10 power minus 1 means 12.32 divided by 10. So it is 1.232 millihenry per phase per kilometer. That was the explanation for this. So let's move to the today's topic that we'll be studying. So in today's topic, what we are going to learn is we are going to understand how to calculate it for how to calculate the inductance for a three-phase line. Okay, so how do we go this? Usually I told you, like it you must have seen 4 in 10 power minus 7, but when we are considering for a three-phase transmission line, okay, so we will consider per phase. So that is the reason I have taken 2 in 10 power minus 7. Okay, any doubts if you are having, you can put in the comment section. I'll explain you, no problem. Okay, so let's move to a next expression. So this was ESE. Okay, so no problem. So my phenomena is you should learn the technique first, okay, then you can solve any problem. But if you don't know how to solve, because engineering is not mathematics, in GATE, in ESE exam, they are not checking how good you are at solving problems, but how well you have understood things. So then once you have understood things, then you can solve any number of problems. You can solve 2-3 problems, and you can solve problems without looking at the problems, and you don't go for the solutions. That is the mistake all the students are doing. Now let's suppose in case of a, now the today's topic we will be studying about inductance of three-phase transmission lines. So we are interested to study inductance of three-phase transmission line. Okay, so basically transmission line. So prior to studying this three-phase transmission line inductance, let me tell you, there is an inductance of three-phase transmission line. Prior to that, let me tell you one thing about the inductance that would be required for us. That is very vital and very essential part. So you must have noticed that there is a concept of self and mutual inductance in case of the transformal transmission line. So there is a concept of self. So you notice this like this. I am making a diagram over here. So the transmission line, yeah. So the transmission line usually uh, is represented by an inductance, and there is a polarity associated with it. So if I draw a dot over here, that means the flow of current is from here to here. Okay, if it was drawn over here, then it was from this direction to that direction. Now suppose the downward dot, okay, on the upward dot I have drawn from here to here, so that means from here to here it will flow, okay. If I draw the other dot over here, okay, here again it is like, okay, it's like here to here, the flow of the current would be like here to here. In other terms, I1, and this is my current I2, and this is the see, this is the self inductance of this wire, and this is the self inductance of this wire. So in between these lines you can see I'll use a different color. This L12 is, this is the mutual inductance. This is the mutual inductance. Now what exactly I mean by these things is that the series inductance per phase, okay, so of this wire would be represented in terms of self inductance of each conductor, okay. So what is that self inductance represent is the series inductance per phase for the single phase two wire line, okay, in terms of self inductance of each conductor and their mutual inductance. So let's consider 1 meter length of the line, okay, single phase circuit by two coils characterized by self inductance are L11 and L22. Now the mutual inductance as I have shown you, okay. Now the flux linkage, that is your flux lambda 1 is linking L11, okay, and I1, and the lambda 1 will, the flux linkage in the wire 1 is due to the self inductance, okay, and due to the mutual inductance as well, and mutual inductance is due to the current I2, it would be L1 to I2, okay. And similarly for phi 2 it would be L22, okay. So L21, here it would be L21, L1, L21, I1. This part over here, I'll rub this part, make it more clear and visible. So this part over here, L21, I1 would be mutual inductance, okay, mutual, and plus L22, I. So this is the self inductance here, okay, self inductance. You can also draw these things, like if you are getting confused, draw the line like this also, okay, okay, like this you can draw. And if your direction of the current IA is like this, for IA to go down the arrow has to be like this, okay, and this IB to be like here, okay, the direction of IB has to be, if it is also going down, so the arrow has to be like this. So this is how it is. And usually what you notice, one thing very important over here, you are seeing, if I connect a voltmeter between this, okay, uh, basically if I connect now I have seen this with this arrangement, what I have seen is lambda 1 is L11 I1 plus L22 I2. So we will see from this particular phenomena, from this particular diagram we can see this I1, okay, is equal to, see, basically from this particular association of this, so the current that is this is the go path and the return path, okay. So the current if it has to be written like this, I1 should be equal to minus of I2, okay, or IA should be equal to minus of IB. So we, from this equation, if we are representing like this, see, this is a magnetic circuit, polarity is indicated by dot symbols as you see, and the flux linkages are there. And here if I'm represented like this, my dot symbol, so I have showed you this is the same direction, this is the same direction. Now if I connect a voltmeter like across, means if this is same load, same thing, if I connect a voltmeter over here, okay, so what would it read, huh? Please write me in the comment section. If I'm joining two inductances, okay, here, and there's one more inductance over here, okay, like this phenomenon, and if I'm joining a voltmeter over here, so this is basically one type of polarity. Now if it was in the reverse direction like this, if I put a dot over here, so that time what it would read, basically in this scenario I1 would be equal to minus I2. And one more important factor is that that means we can replace I1 with minus I2, because in one circuit I1 is flowing, okay. See here in this circuit, if we see the direction of I1 is like this. Okay, it's going like this, whereas in this circuit the direction of I2 is like this because the arrow is like this. So means if it is clockwise here, okay, here it is anti-clockwise. So that's why we can safely say that our I1 is equal to minus I2. So this is very vital part here. And now we can term this in terms of, we can replace I1 with the I2 and or I2 with I1, whichever way you want to replace it, and you can safely write an equation for this particular term, and you can compare this equation with the earlier equations we have derived. So you can safely write in terms of, if you have to write this lambda 1, okay, lambda 1 would be L11 minus L12 into I1, okay, and similarly lambda 2 in terms of L22, okay, minus L21 into I2. So this can be written into I2. So now your LAA, that is, sorry, L11 can be reflected in terms of inductance 2 in 10 power minus 7, which we have seen in ln of 1 by RA dash. Similarly, your L22 would be 2 into 10 power minus 7 ln of 1 by RB dash, which we saw previously. But the mutual inductance that is linking, so the mutual inductance that is linking between two paths, that is L12 is equal to L21, would be 2 into 10 power minus 7, and here it won't be the conductor radius, okay, it would be the distance between these points. The conductor radius is known by GMR, whereas this distance is known as GMD, okay. So in 1 by D. So here we'll be further moving to the next part of the session. So likewise, what the concept of self and mutual inductance can be explained for many group of n conductors. Okay, let's consider suppose let's consider n conductors over here. So I'll draw this here only. Okay, if we are considering n conductors, this same concept, so how it will reflect. So for n conductors we can write down our I1 plus I2 plus I3 if we have many conductors and last conductor IN, okay. Say simple current, all the summation of the currents at a particular point would be 0. So this is for the n conductors, and from this particular equation what we noticed is that our flux that is linking, flux linkage, that is equal to the self inductance Li, I am writing L11 you saw over here, minus Li, the second, if this is 1 is I, okay, I is equal to for 1 and J for 2, so I can write plus L11 Lii and plus, okay, plus summation of, okay, J is equal to 1 to n I J ln of 1 by Dij. So with respect to the mutual conductor, what we found is that with respect to the mutual conductor, what is coming into account? Secondary current is coming into account, and we are also taking into account, sorry, here there is a mistake, yeah. So this is, yeah, here there is a mistake. Lii, yeah, Lii into Ia, Lij into Ij. So this is the secondary current. Yeah, this is the secondary current. So this equation, now let's create a new boards for a clear understanding. I'll again write down this is equal to Lii plus summation J is equal to 1 to n Ij, where J is not equal to 1. So this is because J already I told you the value of J is 2. So from this particular equation we can also write now your I value in terms of this 2 into 10 power minus 7, okay, with respect to the first value self inductance. So I already told you with respect to the first value our GMR, that is 1 by R1 dash, wherein R1 dash is what? It is 0.7788 value of the radius of the conductor, where R is the radius of the conductor, plus here you see for the secondary part this Ij In case of ij, we have the geometric mean radius, which I mentioned, and again j is not equal to 1. So these are some prerequisites before we move to the inductance calculation of a three-phase transmission line. So let's go for the calculation, inductance calculation of a three-phase transmission of a three-phase transmission line. So yes, now let's suppose it is symmetrically spaced. So symmetrically spaced three-phase transmission line would mean you are spacing it at three-phase transmission line. Usually you can see the three-phase transmission system is somewhat like this. Okay, so it is like a circle. The complete circle will give you an angle of 360 degrees. So here there's a phase R, there's a phase Y, there's a phase B. Okay, so between R and Y there is an angle. Okay, so this angle is 120 degrees. Between Y and B there is another angle, again 120 degrees, and between B and R there is another angle, that is again 120 degrees. So an angle A, that is one at an angle of 120 degree, represents A. Similarly, your A square represents one at an angle of 240 degrees. So in the polar form, in the rectangular form, this one at an angle of 120 degree means A would be read as A cos of 120 degrees plus J sine of 120 degrees. So you substitute the values, you get the value. Similarly, A square would be cos of 240 degrees plus J sine of 240 degrees. Now here our understanding, for our understanding purposes, so we have taken a three-phase transmission line and each are equilaterally spaced, so we need an equilateral triangle for this construction. So I am drawing a triangle over here. So this is a triangle, yeah, so nice triangle. So this is at a distance of d, and here also there's a distance of d, again here there's a distance of d. Now let this be conductor 1, okay, and its radius, and there would be conductor 2, conductor 3. So this is A, this is current B, and this is C. So the conductor in an equilateral triangle, the sum of the currents entering and leaving, okay, for a balanced three-phase circuit, that would mean the sum of all the currents leaving and entering for a balanced three-phase circuit. So if IA is the current entering plus IB plus IC, you can write down it's equal to 0 in this case. So only when the conditions are balanced. Balance means the currents are also in all the phases same, and the load which you are going to connect, if at all you are connecting any load. So now from the equations which we have already derived from the equation that earlier I have shown you, that is lambda I is equal to, I'll repeat it, 2 in 10 power minus 7, okay, I, okay, ln of 1 by r dash plus j is equal to 1 and, okay, ij ln of 1 by dij. Nice. So when it comes to the current, so this is a phase IA, okay, with respect to this only the radius will come, okay. When we are taking the current for this phi a and we are calculating for all the phases, so with respect to this IA will come r dash. In case of IB, it will come as this distance dij. So dij is what? Dij is this distance. Dij, you can see, is this, essentially this distance. So now if we want to write an equation over here, we can write safely write our phi a is equal to 2 into 10 power minus 7, okay. Instead of ia dash, it will come as ia, okay, ln of 1 by r dash, no problem over here. Now this is about the second phase. It starts IB, okay, ln of 1 by d. Similarly plus IC ln of, okay, 1 by d. So these are some prerequisites, so you must have noticed it and noted it. So I'll create a new page now. So what we got is, we got the equation here. This is lambda I was equal to 2 into 10 power minus 7. So yeah, we'll rub this part over here. Okay, so lambda a was like, okay, lambda a is equal to, what we saw is 2 into 10 power minus 7. Okay, 2 into 10 power minus 7 bracket 1 by a in 1 by r dash, okay, plus ib ln of 1 by d plus ic ln of 1 by d. One more essential thing what we noticed is ia plus ib plus ic is equal to 0. In other terms, we can, therefore we can write ib plus ic is equal to minus ia. Safely we can write here, what we can do is 2 in 10 power minus 7, okay, ia ln of 1 by r dash, and here this 1 by d 1 by t thing is common, so we can take out 1 ln of 1 by d, and ib plus ic, and instead of ib plus ic we can write that this thing will remain same, 2 in 10 power minus, I don't know what is this, okay, 2 in 10 power minus 7, this is ia ln of 1 by r dash minus ln of 1 by d. So we can say, so that would mean when we are getting this equation ia and minus ia and ln of 1 by d, so if I take this 1 by d up, so it minus will become plus because it's in ln. So it will be ia ln of 1 by r dash plus ln of d. You can write like this, and we know ln of 1 by a plus ln of b, the addition part, so you can write ln of b by a. So on the similar basis here we can write ln of, instead of this we can write 2 into 10 power minus 7, okay, 2 into 10 power minus 7 ia ln of d by r dash on similar grounds. So this was for the circuit phi a. Similarly for phi b we can write, for phi c we can write the same equations, okay. So and because of symmetry and because they are symmetrical, so we can write phi b is equal to phi c is equal to phi a. So and the three inductance are identical, so therefore the inductance per phase per kilometer length is, so here one important concept to remember over here is, see, now that we have gone this up to this, so we are writing our phi a is equal to phi b is equal to phi c, and these all the reactances are equal, and we can substitute here, and for that particular case we can take one value, and we can write an equation straight away that would be equal to, that is your the other cases also, and you can add all these flux linkages your and you can get this particular value in terms of this, wherein you can write your length would be equal to your total, sorry, your total inductance would be equal to 0.2 ln of d by ds millihenry per kilometer. Now what is this ds value? Okay, so where, see, basically r dash I told you is the geometric mean mr, and okay, this ds is nothing but the r dash value only, and it is shown by ds. For a solid conductor this value is equal to r e power minus v by 4. So this we can write like this, d by r dash, so this is in millihenry per kilometer. Okay, this was 2 in 10 power minus 7 was in henry, okay, henry per meter. No, this is for the millihenry per kilometer on a similar grounds. Now if you are calculating the same thing for a different for an asymmetrical spacing, that means all the values of the d are not equal. So that we'll be seeing in the next class, and thank you very much